Okay, so moving to the Lyapunov's direct method now. A system that will be described by x dot is equal to f of x, where f of x is a nonlinear function and n cross 1 vector of nonlinear functions involving different states x1 to xn uh, will be asymptotically stable, or you can say Lyapunov stable. Fine. So if it is asymptotically stable, it means it is Lyapunov stable. Will be asymptotically stable. Uh, so within the vicinity of the equilibrium point, that is the origin of the state, uh, this will be asymptotically stable if there exists a function v of x. This will be a scalar function, rather scalar function v of x, where v of x will be continuous and has continuous first order derivatives as well. So a nonlinear system described by the function x dot t is equal to f of x will be asymptotically stable if there exists any scalar function v of x such that v of x is continuous and has continuous first order derivatives as well. V of x will be greater than 0 for all x not equal to 0 and v not equal to 0. And thirdly, if v dot x is less than 0 for all x not equal to 0. So these three, if this function will satisfy these three conditions, that means it is continuous and has continuous derivatives. It is for x not equal to 0, v of x is greater than 0, and for x not equal to 0, v dot x is less than 0. If these conditions are met, then the system is asymptotically stable. If these conditions are not met, then the system is unstable. So in other words, we can also say that for a stable system, the energy of the system uh, cannot increase with respect to time. So actually condition number third, v dot x is less than 0, suggests that this energy will not increase with time. It will only, the energy will be dissipated with respect to time. Let's take an example and understand this. So say for example, we have a non-linear mass spring dashboard system. So for this mass spring dashboard system, the nonlinear equation will be given by mx double dot plus bx dot uh, x dot plus k1x plus k1x cube equal to 0. So there is a nonlinear spring actually associated with this, as well as nonlinear dissipation of energy. Fine. So you have a system, nonlinear mass spring dashboard system, governed by this equation. Uh, so energy of the system V of x will be given by 1 half of mx dot square plus 0 x uh, k naught x plus k1 x cube d of x. Fine. This is the energy associated with the system. This is k naught and k naught x plus k1 x cube. Fine. Which implies v of x will be equal to 1 half of m x dot square plus k naught x. On solving the integral, you will get k naught x square by 2 plus k1 x raised power 4 by 4. Applying the limits, at 0 there will be 0, at x there will be x. So this becomes k naught x square by 2 plus k1 x4 divided by 4. Fine. So we have this energy function of the system defined by these variables, where x can be treated as x1 and x dot will be treated as x1 dot will be treated as x2. So therefore, Vx in that case will now be equal to 1 half of m x2 square plus k naught x1 square by 2 plus k1 x1 4 divided by 4. Right? So looking at the equilibrium points of the system, x1 equal to 0 and x2 equal to 0, v of x will be equal to 0. Right? So at the equilibrium point of the system, when you substitute x1 equal to 0, x2 equal to 0, taking this equilibrium point at the origin, v of x you can see is equal to 0, and v dot of x will be given by m x double dot. So this becomes 2x2. Fine. 2 cancels out. Plus k naught x plus k1 x k naught x1 k naught x1 cube this mx2 into x dot k1 x plus into x dot, the internal differentiation. So this is your equation. So looking at this equation, you can see, so we need to find out the three conditions that we have defined. One, Vx is continuous. Secondly, you have Vx has to be greater than 0 or all x not equal to 0, and V naught has to be equal to 0. So we have seen at x1 equal to 0, x2 equal to 0, V naught is equal to 0. So this condition is met. Second condition is Vx has to be greater than 0 for all x not equal to 0. So whatever the values of x1 or x2, whether they are positive or negative, Vx will always be positive. So Vx will also be greater than 0 for all x not equal to 0. And looking at this function for x, you can see that v of x will be less than 0 for all x not equal to 0. Energy is continuously decreasing. You can see this is a continuously decreasing energy function. So as far as this system goes, around the equilibrium point at 0, 0, this system is stable. Fine. So we have to actually derive an energy function of a system. So Lyapunov's direct method, what it describes is that you have to find out the energy function of a system. You have to see, and if once you have the energy function of the system, energy of the function, energy of the system, We need to find out whether it's meeting these three conditions or not. If these three conditions are met, then the system is asymptotically stable. That means if it's asymptotically stable, it also implies it is Lyapunov stable. If it is not asymptotically stable, that means it is not. It may or may not be Lyapunov stable. Right? Uh, Now, the so for this example, mass spring dashboard system, we have seen there is a mass, there is a spring, and there is a dashboard. Fine. So this here is actually this is your spring, this is your mass, and this is your dashboard. So the only equation of the system is given. You have the energy function. Find out whether it's meeting these three conditions. So Vx is greater than 0 for all x not equal to 0. V of x, V naught at initial conditions is equal to 0. So that condition is also met. Thirdly, finding out the derivative of this function, you will see that this is a continuously decreasing function. This represents a continuously decreasing function. So if it is, since it is continuously decreasing function, we can safely assume that this system will be meeting our third condition of as well. So this system is asymptotically stable. Now the thing is how to generate the Lyapunov function or the energy function. There can be different methods of generating the Lyapunov function. One will be simply using the energy metric algorithm. You can have the Krasovsky's method. You have the variable gradient method. So you have three different ways of generating the energy function or the Lyapunov function now. The energy metric algorithm, the Krasovsky's method, and the variable gradient method. Okay, so to generate the Lyapunov function now, we'll be studying these three different techniques of generating the Lyapunov function. And once we generate this Lyapunov function, we'll be able to generalize it for any nonlinear system. Before doing that, let's see the properties of this Lyapunov function or the energy function. A Lyapunov function may be positive definite or it may be a negative definite function. A positive definite function will be a Lyapunov function v of x will be called a positive definite function in a given region if at all points in the region it has the same sign. Fine. So if it is positive, if v of x is greater than 0 for all x not equal to 0, then this is called a positive definite function. If in case v of x is negative for all x not equal to 0, then the system is called to be a negative definite function. So minus v of x in that case is actually a positive definite function. So for example, we have v of x equal to x1 square plus x2 square. So for all x not equal to 0, you will see that v of x is greater than 0 and therefore it represents a positive definite function. Similarly, say for example we have v of x equal to minus x1 square plus minus x2 square. So for all values of x1 and x2, v of x will always be negative and therefore this will be in that case a negative definite function. Now, if we have somewhat more complex systems, for example, we have to determine the definiteness of these functions. Q equal to minus x1 square minus 3x2 square minus 11x3 square plus 2x1 x2 minus 4x2 x3 minus 2x1 x3. Fine. So you have this function q. You need to find out whether this can be or cannot be a positive definite, or whether it's a positive definite or a negative definite function. For that, we need to actually rewrite this. Q is equal to x transpose p x. Fine. We need to actually find out the value of matrix P and determine whether this system will be positive definite or a negative definite. So in this case, we have this equation Q. We need to put it x1, x2, x3 something times x1, x2, x3. Fine. So this product should give us back the original function, that is minus x1 square minus 3x2 square minus 11x cube, so on. So you can you have various methods of finding out this matrix. So on inspection, we see that we can find out P matrix to be equal to, for this particular case, we see that P matrix will be equal to this particular matrix. Fine. Now we can actually check the definiteness of P matrix, and from the definiteness of P matrix we'll be able to define the definiteness of the Q matrix. So here we have P equal to minus 1, 1, minus 1, minus 1, minus 3, 2, minus 1, minus 2, minus 11. So to check the definiteness of this matrix, what we do is we apply the Sylvester's criterion. So what Sylvester's criterion does, it takes a subset of matrices. One will be taking this matrix, secondly will be taking this matrix, and third will be taking this matrix as a whole and finding out the determinant. In the first case, the matrix minus 1, the determinant of this is definitely less than 0. In the second case, minus 1 minus 1, 1 minus 3 equal to, this becomes 3 plus 1, that's 4, is greater than 0. And the third case, minus 1, 1, minus 1, minus 1, minus 3, 2, minus 1, minus 2, minus 11. We can find out the determinant of this matrix. This determinant will be minus 49, which is again less than 0. So Sylvester's criterion states that for a system to be positive definite, all the three determinants have to be equal to 0. If any of the determinant is less than 0, then this is a negative definite matrix. So accordingly, if this is negative definite, so will the function Q be a negative definite matrix. Fine. So if xt into p into x is positive definite, so Q will be a positive definite matrix. Fine. Now in case this is equal to 0, then in that case it is called to be, it's said to be positive semi-definite. Fine. And if it is less than 0, then it's a negative definite matrix. So this is about the property, how to determine whether it was energy function, whether it is a positive definite matrix, positive definite function, or a negative definite function. So using this property now, we'll come with another stability definition, and the equilibrium point x equal to 0 of the LTI system, which is described by x dot equal to ax, it is said to be asymptotically stable if for any positive definite matrix Q, there will exist a positive definite matrix P such that A transpose P plus P into A is equal to minus Q. And in that case, xt p x will be the Lyapunov function. So this is actually how you determine the Lyapunov function. So we have described 3 different methods of finding out the Lyapunov function. This is the first method, that is the energy metric algorithm method. So to find out the Lyapunov function of the system, v of x we'll be using the theorems, we'll be determining the positive definite matrix P. For any positive definite matrix Q, there should exist a matrix P such that ATP plus PA will be equal to minus Q for the linearized system of this nonlinear model. And in that case, if this is true, then in that case XTPX will be the Lyapunov function. So we have actually to determine the matrix P. Once we have the matrix P, we'll be able to find out the Lyapunov function. So Lyapunov function Vx will be equal to XT into P into X, and V dot X will be equal to minus XT QX. Fine. V of X equal to XTPX, V dot X will be equal to minus XTQX. And for any value of x not equal to 0, the function V of X will V dot X will be less than 0. V dot X will be less than 0 for all values of X not equal to 0. So the first way of finding out or generating the Lyapunov function using the energy metric algorithm, we define the positive definiteness and the negative definiteness of the function. So from there, if we have the linearized model of the system, we can find out a positive definite matrix P for which this equation will hold true, ATP plus PA equal to minus Q. And in that case, xt into P into X will be the Lyapunov function of the system, and the derivative of this will be minus xt into Q into X. Let's take an example. I have been given an LTI system that's been described by x1 dot x2 dot equal to 0 1 minus 1 0 times x1 x2. Fine. So you have A matrix here 0 1 1 0. Let's take a positive definite matrix Q. So for a positive definite matrix, this has to be positive as well as the determinant of this has to be positive. So Q is a positive definite matrix 1 0 0 1. And as we have to find out actually the matrix P now to find out the energy function. So if we take this matrix Q, for this matrix minus Q will be equal to ATP plus PA. Fine. So that means for any positive definite matrix, we have taken a positive definite matrix here equal to 1 0 0 1. We have to find out the matrix P for which this equation is satisfied. From that equation, we'll actually be getting the value of P. Once we have the value of P, we can find out the energy function. So for this case, minus Q is equal to ATP plus PA. So this means 0, this AT 0, 1, minus 1, 0 into P, let P be P11, P12, P21, P22 plus P matrix P11, P12, P21, P22 into A is 0 1 minus 1 0. This is equal to minus Q. Minus Q means this becomes minus 1 0 0 minus 1, which implies once we multiply these and then add them, we'll get, just check the negative signs, minus P21 minus P12 minus P22 plus P11 is equal to 0, and P11 minus P22 is equal to 0. So we'll be having 4 different variables and 4 equations. P12 plus P21 is equal to 1. We have these 4 equations. We have these 4 equations. Solving for those equations, we will get P equal to 0 0 1 0. So energy function Vx will be equal to then xt Px, where x is x1 x2 and P is 0 0 1 0 into x, that is x1 x2. So solving for them, you will get this is equal to 1 half of x1 x2. Fine. So this will be your energy function for this particular case, and once you have this energy function, now you can determine whether the system is stable or not. V of 0 is equal to 0, that's true. V of x is not equal to, is not less than 0 for all values of x not equal to 0. So for example, you have x1 positive, x2 negative, and in that case V of x will be negative, so definitely this criterion is not met, so it will not be a stable system. So in order to find out the energy function now, in order to find out whether the system is Lyapunov stable or not, we need to find out the energy functions. And for energy functions, then we have 3 different criteria to define whether the system is stable or not. Vx has to be continuous, Vx has to be greater than 0 for all x's, and v dot x has to be less than 0 for all x's. So but for that we need to find out the energy function. To find out the energy function, you have three different methods. The first one is the energy metric algorithm. This is what we have defined here today. We need to find out a positive definite matrix P corresponding to another positive definite matrix Q, for which the theorem ATP plus PA is equal to minus Q is satisfied. And in that case, xt into P into X will be the energy function. So once you have the energy function, then you can say whether your system is stable or not. So that's all for today.